In this video, we're going to talk about sequences and how to do some basic things with sequences on SageMathCloud. A sequence is simply an ordered list of objects. We are going to consider lists of numbers that are countably infinite. So that means we can think of a sequence as a function from the set of positive integers to the set of real numbers. The elements, are also called terms of a sequence, are usually denoted using subscripts rather than function notation. So if we have a sequence as a function f of n, normally is denoted as a sub n or some letter sub n. The sequence itself, as opposed to this is a sub n is a single element, this sequence as a whole is denoted with curly brackets. Or if you want to be more explicit about what n's are available, you can specify n equals 1 to infinity. You don't have to start at 1 necessarily. Sometimes it makes sense to do 5 to infinity, or 18 to infinity, or -3 to infinity, and that notation will specify that. If you don't specify, you're going to generally assume that n starts at 1 and then goes on up to infinity. Here's an example of a sequence: 12, 14, 16, 18, and so on. These are just the even numbers starting at 12. Various ways you could write this. So you could write a sub n equals 10 plus 2 times n for n greater than or equal to 1, sort of writing it out like as a sentence. You could use those curly brackets. Same definition here, 10 plus 2 times n. And if you want to be more explicit about where n starts and where it goes, you could specify that here. And like I said, you don't have to start with n equals 1, so you could call this simply 2 times n for n greater than or equal to 6, or with the curly bracket notation you could specify it this way. Now notice when you don't start at 1, you really do need to specify the n equals 6 to infinity. If you left that out, people would assume you start at 1. Various ways you can define a sequence. In example 1, we saw a list of numbers with some sort of pattern that we could figure out easily, the even numbers in that case. You might also be given an explicit formula for the nth term, and you can also be given a recursive formula that tells you how to get one term from the previous terms. So here, example 2 is just a list of numbers, and the pattern here is that these are all prime numbers. Example 3, we have an explicit formula. The nth term is 3 times n minus 5. And again, unless otherwise stated, we'll assume n starts at 1. Example 4 is a recursive definition. So it tells me the nth term is the n minus 1 term plus the n minus 2 term. So it's the sum of the previous two terms. Of course, you have to start somewhere, so with these recursive definitions, you need some sort of beginning point. In this case, since a sub n is defined in terms of the previous two, we need to define the first two. So a1 is 1, a2 is 1, and then after that, you add the previous two terms. So the third term would be 1 plus 1 is 2, and the fourth term would be 2 plus 1 is 3, and so on. Now to graph a sequence, you're going to put that index variable, the n, on the x-axis, the horizontal axis, and the values of the sequence will go on the vertical axis or the y-axis. In Sage, one way to do this is to use the point command, and if we have an explicit formula, we want to run this point command several times as n varies. One way to do that is to have a for loop embedded right within the point command. We'll do that here in example 5. So here I have an explicit formula for a sequence A. I want to graph the first 50 terms, so I'm going to use the point command, and here's the parentheses for the point command. I want to graph several points, not just one. I'm going to give it a list of points. So to tell Sage to graph a list of points, we use these square brackets. That's the next thing in here. Oops. So there's the square brackets around my list of points. Here's what each point looks like. A point looks like n, that's the x value, and then 3 times n minus 5 is the y value. And I don't want to graph that for a single n, I want to graph that for several n's. So after the definition of the point, I say for n in, and then these square brackets indicate a list of numbers. I start at 1, and then the dot dot says go until you get to 50, and it just goes by 1. So 1 dot dot 50 will give me 1, 2, 3, 4, 5, 6, and so on up to 50. So n is going to range through that list of numbers from 1 to 50. It's going to get plugged into this point, and all of those are going to get graphed. And that's what we see here. We have 50 points, 3 times n minus 5. Now this is just a straight line, 3x minus 5, just with the integer values. Here's another example. So here's the definition of my sequence, an explicit formula. I want to graph the first 50 terms again. So just to kind of save you the trouble of thinking about where things go, I kind of set up this formula. So if you want to cut and paste this block of code and use it, that's fine. If you'd rather just modify example 5, that's fine too. So I declare the variable n just in case I need that. And here I defined my sequence as a function. So sequence is a function, just where the domain is integers. I have this little variable here telling it where to start and where n should stop, and then I have the point command set up. So if you want to use this for your assignment, you can just change the definition of a and change the starting and ending if you need to, and then the point command is all set up to graph exactly that sequence with those starting and ending points. So here's the that example. Alright, example 7, I want to graph the first 10 terms of the Fibonacci sequence, which is recursively defined. So different ways you might deal with a recursive definition of a sequence in Sage. I'm going to set this up using a list. And one issue with using a list in Sage is that a list in Sage always begins with index 0. So the first element in a list has index 0. And our sequence begins usually with index 1. That's the case in this example. I'm going to avoid this issue by just adding an extra 0 in that index 0 position to kind of be a placeholder. So a way to define a list in Sage, you give it a name. I'm going to call it A, and then you say equals, and then you put square brackets, and then I have these 3 numbers. Here's the definition right here in Sage, 0, 1, 1. That defines a list where index 0 is 0, that's just a placeholder. Index 1, which is the first element, is 1. That's because a sub 1 equals 1. And a sub 2 is also 1, and that's why there's another 1 here. Okay. Now I'm going to create a for loop that's going to do this recursive definition. So as n ranges from 3 on up, I need to add the previous 2 terms. So I say for n in 3, starting at 3. I want 10 terms, so I'm going to stop at 10. I'm going to add a sub n minus 1 and a sub n minus 2. Those are the previous 2 terms. I'm going to add those together. I'm going to append that to my list. The way I do that is take the list name, which this one is A, and then I say plus equals square brackets. Okay, don't forget these square brackets here. It says add this number. Okay, this thing is a number. Add that number as the next element in this list A, which is going to be the nth element. Now I'm ready to graph these things, so I went ahead and used the point command again to graph this. And instead of A of n here, to access a specific element of the list, you put the list name A, and then you put square brackets. So A bracket n is the element with index n. Alright, so here is the graph of the first 10 terms of the Fibonacci sequence. Alright, here's another one with a recursive definition. So I want to graph the first 20 terms of this sequence. The definition here, an is defined in terms of the previous term, with starting out at 15. So I get my list set up. I put a little 0 there just as a placeholder, and then 15 in index 1 spot. Now I'm going to set up my for loop. I start at n equals 2, like it says up here. I want 20 terms, so I stop at 20. And don't forget colon here at the end of the for line. And remember, the for loop, you need to indent whatever is going to be run in that loop. So a plus equals square brackets, and then inside these square brackets here I type in exactly this formula up here. Just instead of using subscripts, we have square brackets for these list indices. So a sub n minus 1 becomes a bracket n minus 1. And so I just typed in this recursive formula right there, and when that for loop runs, it's going to fill up this list of numbers, and here's the point command again to plot the points, and there it is. Now I could be a little more efficient and sort of create these points as I go. I've sort of doubled my work by creating the points with one for loop and then plotting them with a second for loop. That's okay. I'm not trying to be efficient here. I'm just trying to get the job done. One thing we care about with sequences is if it has a limit or not. So if the index n approaches infinity and the values of the sequence approach some sort of fixed value, we call that the limit of the sequence. And similar to limits with functions, we write the limit L is the limit as n goes to infinity of a sub n. Now the formal definition is right here. It says if for every epsilon greater than 0 there exists a big N greater than 0 such that this says the distance between the sequence terms and L, the limit, is less than epsilon. So epsilon is any number bigger than 0. I can make the sequence epsilon close to the limit L by taking my n's big enough. So there's some boundary, capital N, so that whenever my sequence terms are beyond that capital N, then my sequence is close to L, close defined by this epsilon. In other words, you can get the terms of the sequence arbitrarily close to L by making the n big enough. Alright, I'd like to explore that graphically with this particular limit. The limit as n goes to infinity of 1 plus 1 over n, all raised to the nth power, is equal to the number e, roughly 2.71828, and so on. We've seen that number e before. Irrational number, so this goes on forever. I set up this little interactive box below, which if it's not working, remember you might need to click on the little arrow here on the left of this line and run this yourself to use the interactive box if it's not already ready to go. What I want to do here, I'm going to put in my potential limit, what I think the limit might be, and this epsilon is the epsilon from the definition. So if I go out far enough, eventually my sequence should be within epsilon of L. So L is marked by this black line. Epsilon away from that is marked by these red dotted lines. So there's sort of these fences. Eventually the sequence should be trapped within these boundary fences from a certain boundary on. Okay, so in this case it looks like my sequence is trapped within those boundaries, so my potential limit L is looking good. Now the definition says not just any one epsilon, but it has to work for any epsilon greater than 0. So if I change epsilon to a smaller number, I still need to see my function trapped within those bounds. Okay, so I went to 0.01 and it looks like, okay, eventually it seems like it's kind of trapped in there. Alright, so that looks okay. Now maybe I should change my index here a little bit. It looked from that previous graph like maybe my boundaries worked, but no, it didn't work. So I've shot outside my boundaries. That's no good. So that means this limit is wrong. Here I have an epsilon greater than 0. I made these little fences, epsilon away from L, and my sequence escaped the fence. That means this limit is not right. So let me adjust the limit and see if I can do better. If Sage will cooperate. Okay, so now with 2.71, this looks better. My sequence is trapped in there now. Of course, it has to work for every epsilon, so if I make epsilon a little smaller, is it still trapped in there? Oh, nope, it's not. And of course, I know this is not the right answer, so I know this has to escape. I told you the right answer was 2.71828 and so on. Let's go ahead and put an 8 here. And I won't do too much of this. Okay, so I haven't reached the fence yet, so I need to go out further. Maybe I'll go out here to 500. Maybe I'll start at 300. And still haven't reached the fence yet. Maybe I need to go out quite a bit more. Let's start at 500 and go to 1,000. And I'll wait for Sage to update this guy. This error is because as I type, it tries to update in the middle when my numbers were the same. Okay, so as I get out here, I see my sequence is starting to get close to this fence, and eventually it's going to get inside there. Now, it's not going to stay in there because this limit's not quite right, so I'm kind of running out of patience with computing in Sage because it takes a lot to go way out here in all of these to the end of this. But you can kind of see what this definition is talking about and how this epsilon kind of makes little fences within my potential limit, and eventually the sequence is going to get trapped in there. Maybe I'll go out one more and see how long this takes. If it takes too long, maybe I'll just go on. But try to plot quite a few points and see if my sequence does end up in that limit. Maybe 5,000 is too far. I might... Oh, there we go. Okay. So, you can tell the sequence is getting close to this limit. It's trapped in these boundaries. And again, I have to be able to make the boundaries even smaller. If I add a 0 here, I don't want to wait for it again, but I'll let you play around with it. If I add a 0 here, I'll get much narrower fences. Eventually, it would escape the fence because this limit is not right. I know what the limit is. Now, if you put E here, you put the number E, it will not matter how far out you go or how small you make epsilon, you'll eventually be trapped in that fence if you put the number E here. I'll let you play around more with that yourself. Now, Sage is able to compute limits sometimes if you have an explicit formula. The limit command doesn't work with a recursive definition, but if you have an explicit formula, you can use the limit command. And I used the letter n up above in my for loop, so if I'm going to use the letter n again, I need to declare it as a variable, kind of clear it out, because when you run it through a for loop, the variable n actually gets assigned a numerical value, which we don't want. So declare n to be a variable, or use a different letter. Limit as of 1 plus 1 over n to the n as n goes to infinity, and it tells me the answer is E. That's the example I was just looking at. So the limit command treats this as if it's a function of real numbers, so it's able to compute it. However, sometimes you might get the wrong answer because the limit as a function of real numbers might not exist when the limit as a sequence does. That's what happens here in example 10. Taking the limit as n goes to infinity of sine of pi n. If I try that in Sage, Sage tells me this is ind, which is indefinite but bounded. We look at the graph, we can see why this limit doesn't exist. This function just flops back and forth forever. As n gets bigger and bigger, it doesn't approach any fixed value. The problem here is that the limit of the sequence does exist, because when you're dealing with a whole number only, pi times a whole number into the sine function gives you 0 all the time. So this sequence is actually just a list of zeros forever. So the limit of the sequence is 0. If we have a recursive definition, the limit command isn't built for that. So I would suggest in that case that you graph it first to see if it looks like the limit exists. If it looks like the sequence just goes off to infinity, then maybe don't even bother. If it looks like it does approach some sort of limit, then our best bet is just to calculate a lot of the values and see where we end up. And that large values of the sequence will be close to the limit. So here's an example of that. If we start out with the Fibonacci sequence that we did before, where the term is the sum of the previous two terms, I wanted to find a new sequence, B. B is going to be the ratio of successive terms in the Fibonacci sequence. So let's look at the graph first. So here's the for loop that defines the Fibonacci sequence. Here's the for loop that defines this new sequence B, and then I'm going to graph it. can see at the beginning it kind of jumps around, but it looks like it kind of stabilizes somewhere around 1.6. Okay, so let's compute lots of values of this and see what happens. So first I set this up to do 20 terms, and this is the answer I got, 1.618 and change. I'm going to increase the number of terms and just rerun this. So I hit Shift Enter to rerun that, and I get 1.618, 03, etc. And if I boost this some more, let's see if I can do 500 in a reasonable amount of time. Okay, good. So here is my 500th term, and by the time you get out to 500, it looks like I must be pretty close to the limit. This thing is kind of stabilized. Can I go to 5,000 without too much trouble? And I don't know if this is even changed now. I think we've already gotten so close to the answer that the difference between the limit and this term is out in the decimal points that we don't see. The actual limit of this sequence is what's called the golden ratio. The exact value is this guy, 1 plus the square root of 5 over 2. Here's that to 30 decimal places, and you can see that this does match exactly what we had with the 5,000th term. In fact, I'm not sure exactly how far we have to go. Maybe 100 terms was enough. Maybe I did way overkill there. So here's the answer with 100 terms. Looks like I'm already there. So this thing converges very rapidly. Now, this is not exactly equal to the limit, but to 30 decimal places it is. Okay, here's another example of that. I have a recursive definition. The nth term is the square root of the previous term, starting out with the first term is 5. So first off, I'm just going to graph 20 terms to see if the limit exists. So I set up my sequence here with the initial 5, and remember I padded the 0th spot with a 0. Set up my for loop to define the sequence, then use the point command, and it looks like this thing is maybe approaching 1. So I calculated 50 terms right here, and a bracket 50, I did this for loop to do 50 terms. This just prints out the 50th term, and it says 1, so at least rounded to these 15 decimal places, it's 1. It looks like 1 is a good estimate for that limit.